Hello, my name is Gungor. I'm a third-year PhD student at the University of Pittsburgh. I'm here to present our research titled Boosting weakly-supervised object detection using fusion and priors from hallucinated depth, which I conducted in collaboration with my advisor Dr. Adriana Kovashka. The depth modality provides complementary cues to the RGB modality, while the RGB modality encodes limited appearance information of images based on colors. The depth modality additionally includes spatial relationships and the geometrical structure of objects in a scene. For the first time, we examine the use of depth in weakly-supervised object detection. Due to the absence of ground truth depth information in most public object detection datasets, we employ monocular depth estimation to hallucinate ground truth depth. This approach requires no additional annotation and it is applicable to any datasets. We explore the relationship between depth and language to propose a specific technique to weakly-supervised object detection. We analyze the characteristics of the objects in terms of depth and the image's context through language to perceive the depth of an object in a specific image. Our method includes a single backbone to extract features from both RGB and depth. It incurs only an 8% overhead compared to the baseline trained with only RGB images and does not add any additional overhead during inference. Contrastive learning enhances representation learning in the backbone, improving its ability to extract RGB features. Following the weakly-supervised object detection literature, we calculate detection and classification scores for the RGB modality. Similarly, we also calculate scores for depth modality. RGB and depth scores are then fused for use in the calculation of multiple instance loss between predictions and ground truth object labels. We calculate depth priors by using the baseline weakly-supervised object detection method to generate bounding box prediction, denoted as capital B, in the training set. Notably, we avoid using ground truth bounding boxes to maintain the weakly-supervised setting. Each predicted bounding box, B, belongs to a category C and the image includes a caption sentence consisting of a various words W. We define a variable D representing the depth value by averaging the pixel inside the bounding boxes. This subscript CW denotes the set of depth values from all bounding box predictions. We calculate the depth range R based on mean and standard deviation of the set. For example, the depth range of a bird object in the context inferred by the word feeding has a smaller depth range, which means closer to the camera, compared to the bird object in the context inferred by word ocean. Further, we define a variable dr to denote the depth range of a specific image for category C. We average the R variable for every word in the caption to obtain dr. As illustrated in two examples, we obtain different depth ranges for the same object depending on different contexts. Note that we only require captions during training. To illustrate the depth priors, let's consider the first example of an object, kite. Our approach calculates a higher depth range for the kite, indicating it is farther from the camera due to the context inferred mainly by words surfing and ocean in the caption. Conversely, the depth range of a kite is calculated as similar, indicated it is closer to the camera in the second image below, due to the context inferred mainly by words man and holding in the caption. After calculating depth priors, we integrate them into our architecture to enhance object detection. We first calculate the depth value of every region proposals. If the value of a region proposal falls within the depth range, the depth mass indicator variable m becomes 1. Otherwise, it is 0. We halve the fused scores if the value is 0. In other words, The attention mechanism reduces the probability of regions less likely to be significant according to the M. Additionally, we utilize depth priors in the OECR module. The updated OECR style mining selects fewer but more relevant proposals based on depth priors, thereby increasing mining precision. During experiments, we refer to the use of only the Siamese backbone with contrastive learning as Siamese only. When late fusion is applied on the top of Siamese only model, it's called fusion. When depth priors are used in the OECR style module on the top of Siamese only, it's named depth OECR. Similarly, when depth priors are used in attention on the top of Siamese only, it's named depth attention. Finally, when all components of method are used, we name it WSOD amplifier. We implement our method on two state-of-art weakly supervised object detection methods, MIST and SOS WSOD, to boost their results. We use two different datasets, COCO and VOC. Fusion outperforms the baseline. With the WSOD amplifier, which includes all components of our method, we achieve state-of-art performance. Note that we cannot use WSOD amplifier method on the VOC dataset as it does not include caption annotations during training, but still Fusion boosts the results. We analyze different components of our method. As can be seen by the underlined numbers, where underlining means outperforming the baseline Siamese only, shows that each component independently boosts the results. When used together in WSOD amplifier, they perform the best. We next experiment with labels extracted from captions rather than using ground truth labels, because it is weaker supervision with no annotation costs. Captions are already present on social media freely. However, the detection performance with labels extracted from captions is worse than the baseline trained with ground truth labels due to the noise. Our approach trained with noise labels outperforms the baseline trained with ground truth labels by reducing the noise. Finally, we experiment on the conceptual caption dataset, which includes noisier captions than the COCO dataset. Our amplifier method successfully boosts the results. Notably, we use the same depth priors calculated in the COCO dataset, but apply them to the conceptual caption dataset. This demonstrates that our depth priors are generalizable across datasets. We qualitatively compare the state-of-art methods MIST, located at the top, with our proposed amplifier approach, located below. In the first image, MIST predicts a large bounding box grouping the objects, while our approach predicts the individual vase objects precisely. In the second image, the baseline MIST faces the problem of part domination due to the some discriminative part of a zebra. Our method overcomes this issue by utilizing the depth modality during training, which emphasizes the geometric variations of objects while comparatively ignoring the complex background. In other images, unlike our method, the baseline misses the object entirely or produces large and imprecise bounding boxes. To conclude, our amplifier method boosts state-of-art methods, SOS WSOD and MIST, without extra annotation or costly computation. Our Siamese network efficiently incorporates RGB and depth with contrastive learning and fusion. Finally, by using the relationship between language and depth priors estimate bounding box proposals that may contain an object of interest.